Starting from the Wigner function, I want to show you what the classical limit is. In particular, let's start from the Wigner function, f sub w. This function is a function of the position, of momentum, and it can also be a function of time in general. Now, for simplicity, I will assume that we are just in one dimension. So, for example, we have a particle with a certain position and certain momentum, and in general, this function can depend on time as well. So we also have the variable of time. The Wigner function is given by an integral of the density matrix, but in particular here we have the density matrix written in the position space. So it's a representation in position space, which is rho of x plus eta over 2. And then the second argument is x minus eta over 2. And then here we might have time. And then we have e to the minus I p eta divided by h bar. And then we have d eta divided by 2 pi h bar. Now, I will do my considerations. I will make my considerations for a pure state. And therefore, this function rho can be written as the wave function psi evaluated at x plus eta over 2. Maybe I can decrease the thickness of my pen, but whatever. So we have x plus eta over 2 t psi star x minus eta over 2 t, like this. And since I want to try to lighten the notation a bit, I will define this psi evaluated at x plus eta over 2 as psi plus, whereas this psi of x minus eta over 2 will be psi minus, and of course I still have the complex conjugate here. So this will simplify our notation a little bit. So whenever we see a plus, we have to associate the plus to x plus eta over 2, whereas this minus will be associated to x minus eta over 2. Simple as that. And what I want to do is I want to find a dynamical equation that the Wigner function satisfies. So we want to take a derivative of the Wigner function with respect to time. And in order to calculate this derivative, we have to calculate the derivative of the density function there. And the density function is also given by this product. So we have an integral of the kind d psi plus dt psi star minus plus psi plus d psi minus star dt e to the minus I p eta over h bar d eta divided by 2 pi h bar. At this point, I have to remember that the wave function satisfies the Schrödinger equation, right? So the derivative of psi plus dt would be the Hamiltonian operator with a plus. So we have to remember that the Hamiltonian is a function of, so it can be considered as a function of space, and it can contain also momentum, but remember that this is an operator. So for example, if we see momentum inside the Hamiltonian, maybe I can try to be a little bit more specific, but let me finish writing the expression. Just wait a second. So I have h plus divided by IH bar psi plus. So this is the expression, okay? The Hamiltonian operator, in general, for just one particle can be written like this. We have momentum squared, but momentum is an operator, in this case, divided by twice the mass of the particle, plus the potential energy as a function of x, of position. So if we replace momentum by its usual expression minus I h bar d over dx, in here the Hamiltonian becomes an operator because here we have derivatives, right? And in general, what we have in here is something that depends on x and on the derivatives of x. That's how we have to think of the Hamiltonian operator. And if we see a plus, we simply have to replace the x with, of course, x plus eta over 2. And similarly, we also have an equation for the derivative of psi minus with respect to time, which is the same as this one, but with the minus here. So we have h minus divided by I h bar psi minus. And if we take the complex conjugate, which is something that appears here, if we take the complex conjugate of this, well, the Hamiltonian remains equal to itself, because if you think about it, when you square momentum, this factor I disappears because I squared is equal to minus 1. And therefore, we can say that the Hamiltonian in this case, if we take the star, is simply equal to itself. But when we take the complex conjugate of this, we get a minus. So here, all in all, we get a minus. And we have to take the complex conjugate of psi minus as well. So this is what we can write, right? And the Hamiltonian, as you can see, is made up of two terms. One term contains momentum, the operator, so momentum operator, and the other term contains the potential energy. So we can rewrite the derivative of Fw with respect to time as an integral of v plus, so I'm going to write v plus instead of v of x, so v plus is by definition v of x plus eta over 2. And similarly, v minus will have a minus here, and here we have a minus. So we can write v plus minus v minus divided by I h bar. And here we have the density function. This density function, remember, is evaluated at this argument here. And then we have e to the minus I p eta over h bar d eta over 2 pi h bar. So this comes from the potential energy in the Hamiltonian, but we also have another term that contains the momentum operator, and it can be written as another integral like this. So we have p hat plus, let me put a plus, remember, so I will be more specific, but just to give you the intuition, here if I put a plus for the momentum operator here, we have something like this, minus I h bar, partial derivative with respect to x plus eta over 2. So that's how you have to interpret this p plus, which is squared because it acts twice. Then we have psi plus, then we have psi star minus, and this is divided by twice m I h bar. This factor I h bar comes from here, and the 2m, of course, comes from this part of the Hamiltonian. Then we have minus psi plus p squared minus psi star minus, and then we have e to the minus p eta divided by h bar, so it's the same as this one, d eta divided by 2 pi h bar. Now the two integrals can be rewritten, that's what we want to do. The first one, in order to rewrite the first one, we want to rewrite this difference. So v plus minus v minus is equal by definition to v of x plus eta over 2. Of course, the potential in general might depend on time as well if we have non-conservative forces. So in here, I'm considering a potential that simply depends on x. So we have a particle that is in a potential field by definition, and by assumption we reason in the case of conservative forces, but whatever. So you can try to be more general and generalize the expression as well for more complicated Hamiltonians, but I will do my considerations. I will make my considerations in this case. So I will simply write the potential like this, minus v of x minus eta over 2. And I want to expand this difference in powers of eta over 2. So basically, I write the Taylor series for this expression. I write the Taylor series for this expression, and then I subtract. You can see that due to the symmetry of the potential field, in particular, you see that in the first case I have plus eta over 2, whereas in the second case, for the second term, I have minus eta over 2. So when I take this subtraction, the even terms will disappear because even powers of minus eta over 2 are equal to even powers of plus eta over 2. Therefore, we will be left only with the odd parts. And therefore, we can write the result like this. We have twice. This twice comes from the fact that the odd parts, the odd terms of this expression, the odd powers, with the minus inside, with this other minus will become plus, and therefore that's why we get this factor of 2. Then we have a summation over n from 0 to infinity. Then we have odd derivatives, which we can write as 2n plus 1 of x. So we have expanded in terms of eta over 2. So in the argument of these derivatives, we have just x. This is just a Taylor series for odd powers. Then we have 2n plus 1 factorial here. The 2n plus 1 is simply due to the fact that we are considering odd powers, odd terms. And then, what else? And then here we have eta over 2 to the power 2n plus 1. And this term, this eta term, since it is contained inside this integral, this eta can be rewritten as I h bar d over dp, the derivative of momentum, this momentum here. So this is due to the fact that if you take I h bar d over dp, this will only act on the exponential, like this. Now, if you take this derivative, what you get is basically eta, simple as that. And of course, if you take the nth power of this, here you will get eta to the power n. So that's the idea. This eta can be replaced can be replaced with this derivative. And that's convenient because after you do the replacement, the derivative can be taken outside of the integral. The integral contains eta, so eta here cannot be taken outside of the integral. But if we replace eta by means of this operator, we can take the operator outside the integral. And this will allow us to rewrite the expression. And once we integrate over eta, what we will be left with will be just some operator that contains p. You see that we have this expansion, and then we will also have some derivatives that contain p, but fw will appear again. Why? Because after you simplify, after we rewrite this expression like this as a power series, we can replace it out by means of this operator, and therefore we can take, it's as if we can take this part outside of the integral. Of course, we have a series, but after that we can, so we can integrate this term here, and we can get back our function fw. So I will rewrite the expression more explicitly later, after I also discuss how to rewrite this part, and then we will find the dynamical equation that is satisfied in quantum mechanics by fw, so the Wigner function. And after we find the dynamical equation, we will be able to take some classical limit, and after we take the classical limit, we will see that indeed we get an equation that is reminiscent of classical mechanics, at least in the case of one particle, because remember that we have one particle in this case, so this is a simplified case, but it's still very instructive, so that's why I want to show you this. So now I want to discuss how to treat this integral here, and in particular I will first consider the integral of this part, multiplied by this of course, and then with a simple reasoning we will be able to find out also the result for this part, and we will put things together. So we are interested in the following term first. We have an integral of the kind p plus squared psi plus psi star minus e to the minus I p era divided by h bar d eta. And I want to view this integral in the Fourier domain. In particular, I will replace the Fourier transform of these expressions, and you will see how. I will show you here. So we can rewrite the integral in the following fashion. Remember that this operator p plus squared can be written as minus h bar squared d over dx plus eta over 2 squared. Then here, instead of psi plus, I have an integral, and the integral sign is already here. I will not write any other integral signs, but remember that we have to carry out the integration, because we will also have other differentials that appear due to the transforms that I'm going to introduce. So I have phi p plus, which is the transform of psi plus, e to the I p plus over h bar x plus eta over 2, which is just x plus, if you want, divided by 2 pi h bar. So this is the Fourier transform by definition. So I define it to be like this, or if you want, the inverse Fourier transform of psi plus. And similarly, we also have a phi star of p minus. Then we have the complex conjugate of something similar to this, e to the minus I p minus over h bar x minus eta over 2 divided by 2 pi h bar. And then we are left with e to the minus I p eta over h bar. I have a differential dp plus dp minus due to the transforms, and I also have d eta. So it's more complicated. It seems more complicated, but actually you will see that this will allow us to simplify the expression that we started from. I have introduced the transforms, but now this operator, the momentum operator, will act only on this exponential, because this is a partial derivative with respect to x plus eta over 2. And let me just remind you that partial derivatives, when you see the argument like this, it will only act on this term, but the partial derivative will not act on x minus eta over 2, for example. So I'm assuming that so the partial derivative of x minus eta over 2 with respect to x plus eta over 2 is equal to 0. But now, so let me cancel this because I don't want to overwrite too many formulas and so on. I want to keep this area quite clean because I want to show you a few things without rewriting the overall expressions, the overall expression for just one step. So instead of rewriting the entire expression, I will just change it a little bit here because it's more convenient. So this second derivative will only act on the complex exponential, right? And when it acts on the complex exponentials, on this complex exponential, what we will be left with, so the second derivative will give us the following. Let me change it in here. So I will erase the second derivative and we can replace that with I p plus over h bar all squared, right? So when we square it, we have a factor of -1 that will cancel this minus, and this h will cancel this h squared. So we are left with p plus squared. Another thing that we can do here, you can see that eta here only appears inside the exponentials. So if we factor all the exponentials that contain eta, we have something like this: e to the I p plus over 2h bar. Then we have plus p minus, and then we have minus 2p times eta. And after we integrate over eta, since this is the only part that contains eta, this part here, which is due to this and this and this. So after we integrate, we get 2 pi delta of p plus p minus 2p divided by 2h bar. So this occurs when we integrate over eta. And if we use a simple property of the Dirac delta, we can also rewrite this expression here. In particular, let me write the Dirac delta of, let's assume that the Dirac delta is a function of x, and we divide x by a positive quantity, a. This can be shown to be equal to a times delta of x. It's a simple property of the Dirac delta, and I will not prove it here. So we can also write this as 2 pi times 2h bar delta of p plus p minus 2p. And after you integrate over eta, you remove the integral over eta here. So we get rid of this exponential, and then we get rid of this eta over 2. Eta over 2 here will disappear as well. And let me put dp plus dp minus here, and here we have 2 pi times 2h bar delta of p plus p minus 2p. And now you can integrate over, for example, p minus. So first let me cancel this. But why can you integrate over p minus? Well, because we want to get rid of the Dirac delta as well. And in order to get rid of the Dirac delta, we must make sure that this other function does not depend on p minus. Well, you can see that p minus appears here and here, but we can use a property of the Dirac delta, which tells us that, for example, if we have a function g of x that multiplies the Dirac delta of x minus a, this can be written as g of a delta of x minus a. So we can evaluate the function at the peak of the Dirac delta. And this can be done if we evaluate this p minus at at minus p plus 2p. And it's quite easy to see this because the peak of the Dirac delta is when this is 0. So we can solve for p minus, and we get p minus equal to 2p minus p plus. So we can replace p minus with this value, and also this p minus here. And then we can integrate over p minus, so we can get rid of the delta that will give us 1, and we would be left with the following. So let's simplify also this 2 pi with this 2 pi, h bar with h bar, and then this factor of 2 with this factor of 2. So we are left with integral over dp plus p plus squared phi of p plus phi star of, we have 2p minus p plus, and then we have e to the I, we have p plus, and then we also have minus with this minus will become a plus. So we have another plus p plus, so we have 2p plus here, and then we have minus 2p, and then we have to divide by h bar, and then we have x like this. So we can factor out the 2 like this, and so let's put 2 here. There is also a factor here, so we have to divide by pi h bar, and this is what we get. Now, this is the expression. I mean, it's something that we obtained with some sweat. We sweated it a little bit, starting from here, and you can see that if we remove this p plus squared, what we have in here is just an integral of rho e to the minus I p eta over h bar d eta, which is exactly fw, but we also have to multiply by 2 pi h bar, which is a constant that appears here in the denominator. So if we start from here, what we get is fw times 2 pi h bar. This means that if we remove, for example, this p plus squared, what we have left is exactly fw times 2 pi h bar. So we just have to remind ourselves that this p plus squared comes from this operator p plus squared in here. Simple as that. Now, similarly, we could have done exactly the same steps, but starting from p minus squared, which acts on psi star minus e to the minus I p eta over 2 d eta, and it's quite understandable. It's quite simple to understand that this expression gives us exactly the same thing, but we have to replace p plus with p minus. This p plus here, though, not the integration variable. This integration variable is different in the sense that we could have integrated out uh, either p plus or p minus at the previous step, but we decided to integrate over p minus, so we are left with p plus. But instead of p plus, in here we have p minus, and p minus is a function of p plus. It's written like this. It's this expression here. So what we have is dp plus times p minus would be 2p minus p plus squared. Then we have phi of p plus phi star of 2p minus p plus, and then we have the same thing, e to the 2I p plus minus p over h bar times x divided by pi h bar like this. This means that since we want to obtain this difference, so we want to integrate this difference here, divided by this constant. And if we call this expression, so let's call it A, we have found basically that we can rewrite A in the Fourier domain, if you want, like this. So we have 1 over 2 mi h bar, and then we have an integral of p plus squared minus, we can also rewrite this as p plus minus 2p squared, phi of p plus phi star of 2p minus p plus, like this. And then we also have a factor of e to the 2i p plus minus p x divided by h bar. In here we have to divide by pi h bar, and we have dp plus, and remember that we also have a factor of 2 pi h bar, included which is included in this expression here. So we also have that. So you have to keep track of a few nasty coefficients, but I hope that the logic is quite clear. After you understand the logic and you know how to do the mathematical steps, you have to arm yourself with a bit of patience, but you can carry out all the things you need to do. At this point, you can observe that, so if we rewrite this, we have 4p plus minus 4p squared, because p plus squared will cancel here, and we have 4p times p plus minus p. But now you can notice that this p plus minus p, since it is contained in this exponential as well, we can rewrite the p plus minus p as h bar divided by 2i d over dx, right? Because if you take this derivative of the exponential, what you get is, of course, h bar divided by 2i times 2i p plus minus p divided by h bar. So this will cancel, and you will be left with p plus minus p. But if you rewrite this operator here, then, sorry, this is not an operator, this is actually a number. If you rewrite this number as an operator written like this, the derivative can be taken outside the integral. So we have something like this. And in particular, you can also take 4p out of the integral, because we are integrating over p plus, and p is not an integration variable, so we can take it out. We have this. We have 4p divided by 2mi h bar over 2i d over dx. And now that we have taken this part outside of the integral, because we have rewritten it like this, and then by using the trick that we can rewrite this difference as a derivative, we have taken everything outside of the integral. But if you remember, after you take this part out of the integral, what we are left with is just the Wigner function. So here we can simply restore the Wigner function like this. And if you do some simplification, here you just have minus p over m partial derivative with respect to x of the Wigner function. And this minus comes from the fact that we have I and I, so I squared is equal to minus 1, of course. Now we are in a position to put all the results together. So we have this part, which is coming from here, that's equal to A. And we have also expanded this part. We have already expanded it. In particular, we have expanded the difference, which we can write like this. And since this part does not depend on eta, after you replace eta with this operator, this will act on the Wigner function as well. So the Wigner function will appear here. And therefore, we can rewrite everything in the following fashion. we have partial derivative of the Wigner function with respect to time, which is equal to, we have minus p over m partial derivative with respect to x of the Wigner function. And then we have plus 2 over I h bar, and this 2 divided by I h bar comes from here. Let me just show you. The 2 comes from here. The I over h bar comes from here. And then after you take it out, when you integrate, you get the Wigner function. So we can simply write this series, and then here on the right, we write the Wigner function, basically. That's the idea. So we have the following. We have summation over n from 0 to infinity, 1 over 2n plus 1 factorial. Then we have the partial derivative with respect to x of 2n plus 1, v of x. So I have rewritten v of 2n plus 1 in this form. And then we have 1 half h bar times I d over dp. And remember that this is raised to the power 2n plus 1. And if I want to finish writing the expression, I have fw here. So here I have the Wigner function. But let me remind you that this comes from eta over 2, right? Because when you take the derivative with respect to p of the exponential inside the expression there, you have you can easily show that instead of writing eta, you can write that partial derivative. So that's the idea. I don't want to repeat these things so many times, but I hope that you understood the message. In particular, I was referring to this eta over 2 here. Eta can be written like this, right? And therefore, we have almost reached the conclusion. We are in a very good position now. We are at a very good point, because this is actually the dynamics of the Wigner function, which is written in a in the general form for one particle in a potential field. But this is for a particle, so we know that the Hamiltonian, and so the classical Hamiltonian, if we think of the classical Hamiltonian as a function of space and momentum, would be written like this: p squared over 2m plus the potential energy, like this. So if you want p over m here would be the derivative of the classical Hamiltonian with respect to momentum, because if you take this derivative with respect to momentum, you get p over m there. And there is also another more formal way to rewrite such a complicated expression. And in particular, since you see that let me rewrite it like this. So I will write v of x in here, and I will show you why. Then we have 2 over I h bar. We have a summation over n from 0 to infinity, 1 over 2n plus 1 factorial. Then we have the derivative acting on the left, so that's why I put v of x here. This d over dx only has to act on v of x, and it's written like this. Then if I put this term here, I have d over dp acting on the right, in this case, because I will put fw here. And then, of course, I also have 1 over 2 I h bar. And this is raised to the power 2n plus 1. Now, why is it convenient to rewrite it like this? Well, because in this case, there is some kind of formalism that will allow us to simplify the expression. This expression here can be written more formally as a sine of 1 half I h bar, d over dx acting on the left, d over dp acting on the right. So the expression can be written like this: dfw dt can be written as minus the derivative of the classical Hamiltonian, and we think of that as a function of x and p with respect to p, Then we have the derivative of Fw, which is also a function of x and p with respect to x. So I will not write the function of x and p, it's implicit. And then I have plus 2 over I h bar. Here I have v of x, but if you recall, since we only have to take derivatives with respect to x when we act on v of x, here we can replace v of x with h, the classical Hamiltonian, which is in general a function of x and p. But since we are just taking the derivatives with respect to x on the left, the derivative of the Hamiltonian with respect to x for one particle, so this is true for one particle, that's equal to the derivative of the potential energy with respect to x. So here we can put the Hamiltonian, and then we have this formal expression with a sign. Let me see if I can simply take this and drag it below. Maybe I can do it. Let's try again. I can do something like this. And then here on the right I have Fw like this. So it's more compact. And this is a special case of a more general formula written by a mathematician known as Moyal. You can check. This equation is also known as Moyal dynamical equation. Moyal is the mathematician. Moyal dynamical equation of the Wigner function. You can check it online, for example, on Wikipedia. It will give you some more details and how to generalize this formula, but that's true for a more general Hamiltonian. In this case, remember that we are studying just one particle in a potential field. So that's how you can write it. And why is this equation important? Well, this equation is important because, of course, it describes the dynamics of the Wigner function, but at the same time, it also allows us to take the classical limit quite easily. So starting from the Wigner function written as an integral that we started from the beginning of the video, it's not really intuitive how to take the limit when we can consider h bar small. Because yes, we have fluctuations due to this exponential, but we can only expect uh, we can only expect the laws of classical mechanics to emerge. But actually, from Moyal equation, it is possible quite straightforwardly, it is possible to show that this equation will become a classical equation. And it's very simple, actually. If h bar is small, the sign, so if h bar can be considered as something small, so it goes to zero in the mathematical sense, the sign can be replaced with its argument. So we have 1/2 I h bar, then we have the derivative acting on the left and the derivative here acting on the right. But this I h bar over 2 will cancel this 2 over I h bar. And what we are left with in the classical limit is this, minus the derivative of h with respect to p, derivative of Fw with respect to x. Then we have plus derivative of h with respect to x, derivative of Fw with respect to p. But now at this point, what is this? In classical mechanics, this is known as a Poisson bracket between the Hamiltonian and Fw. So in particular, this is just a dynamical equation that we have in classical mechanics. In classical mechanics, the dynamics of a certain variable that depends on position and momentum can be written as a Poisson bracket between the Hamiltonian and the function itself. We see that we recover basically the laws of classical mechanics.